Here's. Okay, sometimes. Five. John. You know when you come in, you go in there, because really important stairs.
Hi.
No,
Are they?
Yes, already. Ready to go on. Also, it's like class. That's what I just. One. I want to see what's going on, then I have to get one. Very good. And find something for us. Yeah. If they are. What would be a lady?
Yeah, but it's.
Or did walk and no, that's early moment. So wouldn't be policy or there wouldn't be the or policy given the book like this easy and part of it. Or whatever that right or getting to give them. There's no need I'm saying you said that's not but
I'm sure.
all of these
Hello, everyone. We will probably wait just a little bit longer, so we'll start around 7:05, so about 4 more minutes. I'll give it like 3 more minutes.
Maybe a little bit. It's a little bit time, it's the topic is a little bit different than usual. I am surprised.
Right. And then, right.
Okay, so welcome everyone to the public talk. So if you haven't got a chance already, if you scan the QR code, there's like a small little survey. And at the end, if you put your name under, then there's a chance that you'll win a mug that we have for today. So yeah, welcome to the TSI and Physics public talk. So we're honored to have Susan here, who is a professor in the Department of Mechanical, Industrial, and Aerospace Engineer at Concordia University. And today, she will give us a talk about designing the sustainable aircraft of tomorrow. So right before we start, just a little bit of code of conduct for our event here. So take a read. So yeah, if you have any problem or whatever during the event, such as like if you're feeling uncomfortable, please let me or the volunteer at the door that you saw know. And of course, if you have any further questions and stuff, please feel free to email us at this email address right here. But after that, Susan, I'll let you take over.
Okay, thank you for the introduction. Good evening, everyone. I'm glad to see you. I know this talk is a little different than what you're used to. I think all the other topics I looked at were more going into space. So today I talk a little bit more about airplanes. And I hope you will find it interesting. So that's, thank you for the introduction, by the way. And so I will start just with looking at some pictures here. And the question that I would try to answer today is, what does a truly sustainable aircraft of the future look like? And how do we make it work? Okay. So the picture that we're looking at here depicts some beautiful futuristic concepts. And what is interesting about this picture is that these are actually the airplanes that NASA has foreseen that we're going to be flying it since of last year. So I think most of you, if you have taken the aircraft recently, it looked rather like this at the Montreal airport. So this is one of the greatest and latest airplanes that entered service a couple of years ago, designed by Bombardier. Initially, now called the Airbus A220, and it really looks pretty same. Oh? It doesn't look like this at all. So the question that I want to explore a little bit this evening is, what are the barriers to making these beautiful, very efficient concepts work, and what are the challenges we have? Okay. So my flight plan for this talk, I always have a flight plan as every aerospace engineer. We're going to start with a little introduction about talking about these challenges. And also because I think most of you are not in the field necessarily of aerospace engineering, maybe more in physics, as I suppose. I will bring you up to speed about some of the things that I work about in aerospace engineering, which are very applied physics. And then once we have the necessary knowledge, we're going to look into two case studies that highlight some of the research advances that we worked at, and that will maybe help us to accelerate a little bit the maturation of these advanced concepts. And then at the end, I'm going to talk about what's next, what's coming up. So why do we need to rethink the aircraft that we are all flying in today? And what is the driver for that? So, slides. Good. We need to, a lot of the drivers today are regulations regarding reducing emissions and the environmental impact of aircraft. So this has been around for a long time, so that people try to investigate solutions to reduce the environmental impact of aircraft that are mainly emissions, pollution of the air, but also emissions in terms of noise. Aircraft use a lot of land for the airports, but also for the aircraft are not recycled. They are stored in these graveyards, which take out a lot of space. So we produce all sorts of waste. And also a lot of the concepts for reducing emissions, for example, reducing biofuels or what we call sustainable aviation fuel, will require that we use lots of land to plant crops that we're going to transform into fuel, which is also not the most sustainable solution, maybe. So, but there is a renewed interest, and there are always targets to reduce the environmental impact of aircraft and aviation, and that drives a lot of the advanced design activities. Just recently, the targets have been renewed, and now we're targeting net zero CO2 emission by 2050. So this is very ambitious. But that's also what makes us work and think about it every day. So what are the solutions? What are the different aviation solutions we imagine to meet these targets? So there's a mix of things. So what I already talked about here at the top right people think a lot about alternative fuels, so sustainable aviation fuels, for example. But also more recently, people talk a lot about hydrogen propulsion. So this is a concept from Airbus showing an aircraft with hydrogen tanks. This also is not new. People have already worked on hydrogen-powered aircraft long time ago. I think in the 70s, there was even a demonstrator flying developed together by Airbus in Germany and with a Russian company together. So there is, this is not a new concept, but recently with this pressure about reducing the emissions, hydrogen is again an option on the table. Then we have many investigations in what we call hybrid electric aircraft and aircraft with distributed propulsion. Here you see two examples on the top. This is a project, a Canadian project from with Pratt & Whitney and other people looking at making a hybrid electric version of the Q400, which is a very popular Canadian airplane. And below you see a little bit more advanced concept from a company from the Netherlands, Elysian Aircraft, looking at having these distributed propellers here at the wing. They are all driven by electrical power. Then we have this unconventional configuration. You see on top Bombardier's EcoJet concept and the Theodel Flying V, which I'm going to talk about a little bit more later on. On top of that, we want to make the systems more efficient that are in the inside, and there are several investigations in increasing autonomy and automation in airplanes, especially also to improve the flight path and increase the efficiency of the flight operation. So all these different concepts come with different challenges, and I will explore them in some more detail later on. But first of all, there was a, okay, this is nice. Okay, first I just want to give you some background about why is it so complicated. So what I think you know as physicists, most of you know how airplanes fly, okay? There is a lot of magic involved about what's happening with the different airflow around the surfaces and so on. But for sure, what we need to consider are the force balance on our airplane. If it looks conventional or unconventional, we need to respect the physics. So typically, in order to bring our airplane in the air, we need to generate lift. We generate the lift by moving the aircraft forward through the airstream by producing thrust. So if we move fast, we have more lift. And also if the aerodynamics engineer worked very well, we have a very good aerodynamic shape of the aircraft. We can generate a lot of lift. So thrust is generated by the engines, and it's also there to overcome the resistance of the aircraft in the air, which we call the drag. And of course, our lift needs to be big enough to overcome the weight of our whole machine that carries all the necessary equipment that we need to make our aircraft fly. So if we now want to modify the aircraft, and most of these advanced concepts that you have seen at the beginning, they are concerned about the aerodynamic efficiency. So these beautiful concepts, they try to optimize the lift to drag ratio. So most of the time, we want to create more lift with the overall surface and reducing the drag. And so in this case, if you do that, you might need a little bit less thrust to fly at the same speed. Yeah, so that's the premise. Okay, so we burn fuel to propel our airplane forward. We also need some energy for all the systems inside the aircraft that we need to make work. And this is what I'm gonna delve a little bit deeper in a few minutes. And also we take some energy from the outside. So typically we need to do some cooling inside the aircraft. For example, if we have a more electric propulsion, it needs a lot of cooling. So we put some holes in our beautiful aerodynamic shape to get some cold air from the outside. And this again increases our drag. And of course, we're gonna exhaust some stuff to the environment. So just to say, what is really important when we talk about an airplane, it's typically like what we call a flying compromise. Okay, so we can improve the lift of our aircraft, but then we might, for example, end up with a very heavy structure that is very difficult to design or cost a lot. And also it could be heavier, and then we need again more thrust. So every time we need to make a change on our airplane, we need to consider all these aspects together. So, yes. And so typically when you look at these beautiful advanced concepts, they are more concerned about the aerodynamics and the propulsion systems. So one of the things that is typically a little bit less investigated is everything that we need to put below the structure and the beautiful skin to make our aircraft work. And this is what I want to talk a little bit more about, because this is what typically makes the aircraft development process very lengthy and very complicated. And yeah, so this picture shows, it's like an X-ray of one of the biggest and most complicated aircraft, the Airbus A380. And it shows already a little bit what we can see all below the skin. So lots of wiring, piping. We have the fuel system that provides the fuel to the engines. We have electric wires and a lot of avionics boxes. So these are all the electronics that are used to navigate the airplane, to control the engines, for example. We have hydraulic system, environmental control system, air conditioning, etc. So many different systems. They are all connected, and they all need to fit in this shape that we define to make our aircraft work safely. So now I'm going to talk a little bit more about all these systems that we need to fly safe. And why I'm going to talk about it, because this is really important to understand, because this will make our new aircraft concept work or not work. So typically in an aircraft, we have different systems, as I said, so we can classify them in different categories. So the first are the systems that fulfill the basic functions of our aircraft. So we call them, and they consume some sort of power. So for example, the flight control system will move little surfaces on the wing to control the direction of the aircraft. We have the landing gear systems to safely land. We have the avionics, as I said, they are there to navigate systems in the cabin, to control the environment, the temperature, the pressure, make sure we survive when we fly up there. We have the fuel system to distribute the fuel to the engines, environmental control I talked about, and ice protection as well. So this is just a few of them that are typically in an aircraft that we use to travel around. In order to make those work, we need different power systems that they use. So typically we have hydraulic systems, electric systems, and pneumatic systems, and they receive power from the aircraft engine. We typically have an additional system, which is called the auxiliary power unit, which is used on the ground or in failure scenarios. And we always have our last emergency power device, the ram air turbine, that makes us land safely even if the engines fail. So typically, just to give you an idea on how this whole works, we have the fuel system that will provide some fuel to the engines, and the engines provide thrust for our aircraft to advance, but also provide some mechanical power to drive an electric generator, hydraulic pump, and they provide some compressed air to our pneumatic system. The hydraulic system then will deliver power to actuation systems like the flight control and the landing gear, the electric system to avionics, cabin, etc., fuel pumps, and we have some systems that run on pneumatic power. So on the ground, as I said, we're going to use the APU as well. It also uses fuel, and the APU will be used to power some systems on the ground, as I said. We also use it to start the engine. And if you want to start it, you will use electric power. So you're going to see this will become even more complicated. We have some emergency power supply, and we typically use the air from the outside for some cooling and other functions. And this is important to consider because this is what creates the drag on our airplane. And if we need more of that, because we need to cool more because we have an electric propulsion system, so then this is important not to forget. So each of the systems generates some heat that goes to the environment or need to be cooled by the systems inside the aircraft. And sometimes we have so much heat that we need a dedicated cooling system. And recently, most of these aircraft systems are getting more and more electric, so all of them use a little bit more or less of electric power. In future configurations, we might use a fuel cell as a power device, with some alternative fuel and so on. So this is just to illustrate you that there's a lot of complexity going on under the skin of the aircraft. And if our, the conceptual designer and the aerodynamics people come up and say, oh, we have this beautiful new concept and it looks nice. As a system engineer, my first question is, okay, how can we get all this stuff in the aircraft? How can we make it work? You have to consider that about 30 to 40% of the volume inside the aircraft are filled with this equipment. We need it to make the aircraft work safely. We cannot just, minimize it and fit it in some aerodynamic shape. So this is why it's important to have some consideration of that. And this is also the reason why a lot of the advanced concept projects after this initial concept phase, and when you start looking into that, either they get delayed or they say, oh, we are not there yet, we go back to the drawing board, and this is when these development cycles become very long. All right, talking a little bit about that, and then I'm done with the introduction. How many of you know how much time it takes to develop a new aircraft from scratch? Any idea?
10 years.
That's a pretty good guess. Okay, this is when when everything goes well, I would say. The thing is, there's a hidden part about the aircraft development that is when people in secrecy, look at all these advanced concepts. But typically, we have 3 major phases in the development process. Conceptual design, this is where we develop the concept. Preliminary design, and this is where traditionally we start to look at all these complexities. And in the detailed design, we just build it, and then we hope it works in our first flight. Typically, it's a year at least until we get the certification. So that means we can say this aircraft is safe, and then afterwards we can enter into service. So this is typically a very long process. And a lot of these advanced concepts, they kind of get, I would say, stalled from this transition from conceptual to the preliminary design. Somewhere in between, there is what we call the launch of these of the project. This is where the public will get know about it. But sometimes you spend already many years here just ahead of time. So typically, in parallel to designing new airplanes, this is the game of the aircraft manufacturer. There's many different companies, universities developing technologies that we eventually can use, and their market analysis and all that need to work out together, in the beginning to say, okay, this aircraft that might make sense, that will it's worth investing a lot of money to develop it. And so because of a lot of these very promising concepts that we have seen that promise a reduction of fuel burn of 50% or something that look very interesting, because they kind of typically either get even heavier or unfeasible when we go into these detailed phases. This is why we try to put some of the system details in the earlier design phases. So this is basically what we call system architecting, and this is what I'm looking at in my research program, to not being the person that say, oh, it doesn't work, but to develop tools and processes that we can use early on to develop concepts that work and that will actually make aircraft more sustainable. So in order to do that, there's a couple of research axes. I will not go through all the details, but basically we're looking into different process improvement, and we're looking into developing models and tools, and also investigate some new technologies that could work together. And we do many different application studies on advanced concepts, and I'm gonna talk about this flying V concept here a little bit today, but it goes beyond airplanes, maybe even space in the future. Okay, so what makes the sustainable design even harder, as I said, is that there are many aspects, many things change. So first of all, we're gonna have more integration between our propulsion system and our system architecture. We're gonna have many, many different options that we can investigate. So it's harder to choose the best solution. We're gonna have complex systems, and because the shape of the aircraft changes, it's more complicated to place them in the aircraft. We're gonna have high power, high voltage, and safety certification challenges, and more thermal management problems. So I will talk about only a few of them today, maybe the last two ones. But yeah, that was just to put you into context about the rest of the talk. So I think already what we have learned so far is that these new aircraft concepts and the propulsion, new propulsion systems, they seem very promising, but they create more challenges in the system development, especially complexity and also new safety questions. And this is the first thing that I'm gonna address in the first case study that I'm gonna present. All right, so we're gonna talk about the so-called flying V aircraft. This is a very innovative project, has been developed by the TU Delft in the Netherlands. And it was proposed, the first concept, in 2014, so it's already a couple of years. And there's a lot of different research activities going on, especially in optimizing the aerodynamics and the stability and control. So this aircraft has many challenges, but the premise is that it can reduce the fuel burn by 20%, at least compared to a comparable aircraft, because it has a very integrated design. So if you look at the inside, the cabin is kind of integrated into the wings, so we don't really have a fuselage per se. The whole shape is aerodynamic, and it's a very efficient use of space. So now let's have a look at the systems aspect for this aircraft. So we're going to compare it to a conventional one here. So this aircraft is directly sized in terms of performance and passengers as the Airbus A350, which is a large aircraft that you would typically use if you fly across the ocean. And so the first thing we can already notice is that, yes, we have a different shape of the fuselage and the wing. Overall, we use less area, so this is why it's so advantageous from an aerodynamic perspective, but we also have a very different cross-section of the cabin. Okay? So typically, we store all the fuel for the aircraft in the wings. And we have some space for cargo and avionics underfloor in the nose and aft areas, also for the hydraulic systems and air conditioning. They are typically somewhere in the zone under the floor. And we have a tail here for the APU. So typically we have enough space under the floor, in the wings, in the wing fuselage section and the tail to put everything we need. When we looked at this airplane here, the designers initially already foreseen some space for cargo here in the back. So this is good. And the fuel is already a little bit more difficult. You see all these pink areas are designated for the fuel, which means if you're sitting in this part of the fuselage here, there will be actually fuel on the side. So you cannot look out of the window and say hello to the neighbor sitting over there, which would be really fun. But, you know, you will just looking through a fuel tank. There's limited space below the floor, as you can see here, very small. So no space really to locate any, you know, air inlets, air conditioning system, hydraulic base, etc. So that's the first thing. There's not much space, so the outer shape has a big impact on the inner space. So we looked at that and see, okay, how can we find solutions to make it work? There's also no tailcone for our APU. So one of the things that drives the system layout as well is the safety. So each aircraft needs to withstand a certain number of threats. And the safety, there's different analyses that are done. And typically, one of the analysis is to look at the survivability of the aircraft on the different threats. So for example, a bird strike, lightning strike, fire, ice, and also releasing of fragments, for example, from the engine or from the tires that could impact the aircraft and hit some components. So these analysis, we call it particular risk analysis, that guide the layout of the system and components. And because there are so many rules and regulations, and it's difficult to do that quickly in conceptual design, so we computerized all these methods in a code that can run very quickly, and we can use that in conceptual design on a very simplified aircraft shape, as you will see here, which will allow us to make a quick analysis early on. And so I will just show one aspect of that. So one of these analysis is what we call the engine rotor failure. So a little fragment of our engine gets loose and with infinite energy will hit on a trajectory through the aircraft. The trajectories are these red circles that you see here. And you see on a conventional aircraft, you should not sit between the engines. This is the first thing, but typically there's many, you know, from one engine to the other, there's the fuselage in between and so on. So there are some elements that will absorb some of this energy. If you look at our flying V aircraft, we see already that between the engines, there's nothing in between. So typically if blade of this engine gets loose, it will hit the other engine most probably. So both of them will fail right away if you don't put something in place, and this is not good, okay? So there's many other issues we discovered through doing this different analysis, but you know, this is one of them. So we have, so we can have potentially loss of thrust. We can make a hole in our cabin, so we lose the cabin pressure. And also the routing of a lot of the system that goes here through these different areas, it will be difficult to separate that and so on. So this initial analysis already showed us many challenges, and this was very interesting for the researchers on the flying V. So you know, they were discussing some solutions. They are not disclosed yet, but you know, it's just very interesting that you can use this kind of very fast analysis, and you can actually combine that in the future with an aerodynamic optimization to already get a better configuration from the beginning. So just some lessons from this study here were there's some safety risks that need to be addressed for the engines, for the fuel tank placement, for the routing of the hydraulic system, and protection for cabin depressurization. So the conclusion is our conceptual design tools, they help. And there's more work, okay? So there's more work for the integration of the systems, the distribution of the avionics. Potentially, there's a lot of maintenance complexity that needs to be addressed, routing of systems, etc. So there's more work required. But this was just an illustration on how these automating all these complicated rules that are in thousands of lines of regulations, putting them into a code enables us to use them in early design. And so we can spot some problems early on and then act on them and actually maybe develop a solution that will work in the future. All right, so now we have all these, some systems placed in the aircraft. Another aspect that is typically very critical early on, especially for if you go to electrified aircraft, are thermal systems. So we can put all the systems in, then typically they are tightly packed, and then we're gonna have problems because they overheat. So then there's two options typically. Either we go back to our aerodynamics colleague and put some holes in our beautifully designed shape, or we try to address that earlier on by maybe finding another solution. So the second part of the second case study I'm going to show you is that we try to address these hidden thermal challenges that we also typically find out only in the later design stages. How can we address them also earlier? Very similar to our safety assessment. So there's two things we looked at. First is to develop some kind of simplified geometry that we can use to run a faster thermal analysis that is typically done, which we call CFD, computational fluid dynamics. We use that a lot to analyze it, but it requires a lot of details, and so we try to simplify that. And the other thing that we tried to do was to develop an approach that doesn't need very long computation of thermal analysis, and we call it the thermal risk assessment. So this is what I'm going to talk about. So the introduction of this thermal risk assessment is basically just a quick check, very similar to the safety that I have shown, and to show the potential non-compliance with thermal requirements, meaning is there something that could potentially overheat, and we want to either find a better place for it, or we need to foresee some good cooling strategy right away. How we do that if we don't have a lot of information? We created a simplified method using basically non-dimensional relationships from thermodynamics to analyze the aircraft thermal environment. So what is the environment outside? So this is a portion of our aircraft. You can see how hot it is outside, what's the ventilation around it. We have the simplified view of all of our systems. We represent them through some shapes and adding some heat loads to them. And then we're going to put them in a bay with different ventilation access and some information. And we want to come up with some kind of quantification of which system has a high risk of overheating and a low risk or medium. And this, again, can inform the overall conceptual design process. I will show a little example of how that works. So this is an example of a typical business jet aircraft. In the aft of the aircraft, we have this aft equipment bay, which is full of equipment, hydraulics, air conditioning, pumps, whatnot. And so this is a little bit how it looks like in a 3D model later on, and we simplified all these components and the simplified shapes. And the case study here was to investigate for this electronic box that is there to control the engine. 3 different locations, one here, one here, one here, and just to see what is basically the best location from a thermal perspective. So again, our little tool just considers what air goes in, what air goes out, some key parameters, and it will give us this very simplified picture of our bay, and it will give us some measures to say which component, which component location is better. So you're asking, what does it have to do with the aircraft of tomorrow? So as I said, most of the configurations really have a very optimized shape. So typically the systems will all be much more closer to each other. Also through the safety constraints that I mentioned before, we need to put them in different locations. So analyzing safety and thermal aspects at the same time will really help us to get good solutions. And we're actually having a research project at the moment that involves also a professor and students from McGill on what we call optimizing the system configuration for this future aircraft, where we bring together all these different tools and we let them help us to find a feasible solution. Good. Checking time. Okay. So these were these 2 case studies that I wanted to show you. And now, what's next? So basically, as I said, we work a lot on developing tools, and they will all be integrated in this big design framework. You just see here a couple of boxes and so on. And so typically we consider the overall aircraft design, propulsion structures, but then we have these different systems here, and we integrate all these different tools. So safety, thermal aspects, wire routing, maintenance, all these different things. We try to simplify the models, integrate that into a common framework. So we can run quick trade studies of these conventional configurations early on, and to find some solutions and to find aircraft configurations that work and also reduce the environmental impact. In addition to make it work, there are some additional activities that we focus on in order to improve the process, which all are related to digitalization of the certification rules, better analyzing the environmental impact by looking at the whole life cycle. So these are few things we need to do in parallel. But we also develop tools to investigate the technology of tomorrow that you have seen in these beginning slides. So for example, at the moment, we are working on developing all the tools and estimation methods for hydrogen-based propulsion. So how to size cryogenic hydrogen storage tanks that can go into the aircraft, heat exchangers, and so on. So it's a whole new world that we want to integrate. We work on some projects more with solar energy to retrofitting the fleet of existing small airplanes that we use in Canada to fly between all our different lakes. And also we work on some concept for advanced cockpit configurations. So these are all just different application platforms where we develop the tools, and the idea is to combine them all together so we can come up with some more feasible, promising concepts. And the question of today is also, we're going forward, how can AI help in all of these topics? So this is really what we're going to be looking at the future. There's different aspects that could be interesting. So one is a lot of the problems we have in our detailed design tools is that they take a lot of time to run and to compute. So we can use some AI tools to make them run faster, optimize our code. That is critical. We can also basically get a lot of more data to build better models. And we can also implement all these many design rules in some kind of a virtual guide to the aircraft designer. Okay, so this is also these are some areas we're investigating going forward. So that is already the end of my talk. I hope you learned a little bit that not how airplanes fly, I think this you know already, but there's a lot of magic involved, and we need to do a lot of magic to develop airplanes for the future that not only look fancy, but are actually reducing the environmental impact. And in order to do that, there's a lot of magic inside the aircraft that needs to happen. And I hope that in the future, I don't know how it will look like, the airplane of the future, but I hope it will help us to keep our skies clean. And in the meantime, while waiting for that, we can either do a lot of work, or we can also pack our suitcase very light, not to use too much fuel when we're flying around. But yeah, it will be an exciting journey. I will be happy to answer your questions. But just before closing, nothing of this is happening without a big team of collaborators and researchers. So a big shout out to my research team who helped to do all this work and produce some beautiful pictures for my slides. And also our collaborators. We have many partners in Canada and Quebec, and our funding agencies, and also our international partners that work on these interesting projects. With that, I'm open to answer your questions. Yes.
For the flying V, you said that it's harder to find places to store the fuels. So do you think that plane would be more used for shorter flights, like less than 5 hours, compared to long into?
This airplane is really designed to do the longer flights, because we will be able to find enough space for the fuel. It's just, you can always scale up the aircraft a little bit. You can also just put partitions in the fuel tank. So there's different options. But typically all these options lead to some additional weight, or, let's say if you scale up the whole aircraft, you're going to, again, it will be heavier and so on. So it's just it's just tricky, I would say. But yeah, so initially this type of aircraft, they look very efficient. They are really designed for very long missions. But yeah, there are other technologies as well that might be used to help to reduce the amount of fuel. So for example, more efficient engines, you might also need less space for the fuel, for example. But yeah, this is all, like, all the things are connected basically, and the idea is just, if you do one study after the other, it will take forever. So you need to kind of combine it together. Yeah. Good. Other questions? Yes.
Do you think we'll see an airplane like the Concorde in the future?
You mean a supersonic?
Yeah.
Yeah, there are already some studies from NASA. They worked on a new supersonic airplane. The issues is there's some issues with the sonic boom and so on, but they developed a new technology to reduce that. So that's promising. At the same time, if the aircraft fly very fast, they also burn lots of fuel. So it doesn't really help with reducing the environmental impact, unless you have a hydrogen-powered supersonic jet or something. But yeah, so this is definitely in the future concepts. It always shows up somewhere, because there is some interest of having a very high-speed transportation. There are also some other concepts that are more space planes, so not necessarily flying supersonic through the atmosphere, but doing these kind of parabolic flights through space, hyper space. So this is also more fancy. I'm also not sure it will reduce the environmental impact, but yeah. Other questions? Yeah.
Do you ever take inspiration from nature, like, for example, the feathers of birds, owls, to reduce the drag on the wings or make it more quiet?
Yes, there are several projects on that. So one is, for example, for the skin of the aircraft, so to reduce the friction. So there are some project to imitate the skin of sharks, for example, and so on. So there's some bio-inspired activities. It's out of my research area, but I don't know about them. But yes, so that's for for example, for the skin friction. Then for the we have all the flight control surface to control the aircraft and flight. So, and there's some project of having some more morphing wings, or inspired by what birds are doing. So, and not having just deflecting the surfaces in discrete settings, but using it to optimize the configuration. But all these, this is very complex. And especially it's very complex to make it work safely. And if you want to make it work safely, then you need to have what we call a lot of redundant, so many separate controllers to make it all work. Typically, the aircraft becomes more heavy again, and so on. So they're interesting. This is what I say. There's always interesting promises and where we can get. But then, if you want to make it work, especially for aircraft transporting people, this is where typically gets back to the reality. It's a little bit, but yeah, it's good to be inspired, I think. Yeah.
Virtually every passenger aircraft that actually flies looks like data.
Yeah.
Like, so like taking these parameters, you end up with the airplanes that we have like that.
Not necessarily. I think this is what we wanted to get at. So the airplanes all look very similar because we found something that works. And because everything inside is so complicated, people just try to do little improvements on the outside and improving the engines and so on. But now this is kind of, we cannot get much more out of that. So we need to look into new configurations of the aircraft. But this comes with the whole work of rethinking everything we put inside. I think there might be some interesting other configurations. It just requires that really all the disciplines work together to find a solution. And but it's not an easy task. But I would say it only because all the aircraft today look alike doesn't mean that this is the only solution that we're gonna have. I think I hope there's something else.
I like the in fact, biplane design.
Yeah.
Who's looking into that?
Which biplane design?
Oh, the one with the double set.
There are different. So this, I think, was a concept. I think it was also. There's always different universities, so MIT with Boeing and so on. But there's also in Europe we have an organization called Bauhaus Luftfahrt. They're also looking into these. We call it the box wing design. So there's different. Many different universities, research institutes always investigating that. It's interesting, but also again we have there's always challenges. But yeah. Other questions? Yeah.
I find it interesting that the very simple design of our current planes seems to be quite optimal, and improving significantly beyond that requires a lot of thinking and engineering and complexity. That's pretty good. So we already have a good start in these.
Yeah, I mean, it has matured over all these years. So, this is also how the industry works. So you, like, from every accident, every problem, you put it in the regulation, you try to make it better and so on. But this is also all driving them to the same solution, because for each new aircraft, you need to show that it meets at least the same standards that we have today. And if you deviate from a current design, so then it's difficult. So yeah, it's interesting.
The comfort of the passengers certainly plays a role in the overall economics of a project like this. But I wonder, is there any interest for separating parts in the industry?
Yeah. I actually, on one of my pictures, I have a picture of the flying whales airship. So at the moment there are some companies looking into that, mainly for transportation of goods to remote areas and so on. So this is a new, not new, it's in the recent years has get some traction. I think also some fewer investigations for passenger transport. But for transportation of large equipment and so on, this is there's actually a company, a French company that's now established also in Quebec called Flying Whales that looks into that, and they're also investigating then all these new propulsion technologies and solar and electric propulsion and so it's definitely not off the table.
Do they pose the risk?
This is more like a hydrogen problem, I would say, but yeah, so there's some, yeah, I mean, this is always there, so this is why you also need to do safety analysis and everything for that, so, but yeah, it's, yes, we see a lot of diversity again, right? Now that we are like, we cannot do much more with the aircraft we have, so people also think, okay, maybe we use different vehicles for different type of missions. Yeah.
I think a lot of these images we see are conceptual studies seem to be from universities or like research facilities, but I didn't see many from manufacturers actually. I mean, why is that? They are Airbus and Boeing, do they have the same interest investment in these new configurations than you do in research or?
Yes, but I picked some of them. So, for example, recently Bombardier, our Montreal-based aircraft manufacturers, they heavily advertised their EcoJet aircraft. So this is also a blended wing aircraft. But typically, these airplanes are, they work on them in secrecy for a long time before they publish that. So, for example, this is when I came to Canada, I worked for Bombardier on this airplane that was in 2009, and I think they first officially announced that they're working on it in, I don't know, a few years back. So, and so, it's like they are doing stuff. Boeing works a lot with NASA on these advanced concepts. So most of the NASA concept that I showed, they have some involvement from Boeing, and also Airbus. There's pictures out there. So one of the hydrogen aircraft that I showed. So they are all publishing from time to time these futuristic approaches, but I think and they're developing technologies, but a lot is done in collaboration with the universities and research centers. Yeah, because it requires just really a lot of investigation before you can say, okay, this really looks promising, we're gonna invest in that. But yeah, a lot is behind the closed doors and you don't necessarily. Yeah.
And we spoke of passengers.
Mhm.
I see we consider very revolutionary design like this flying V, but we're still thinking about passengers sitting down.
Mhm.
But if we're going to sit next to fuel tanks and without windows, that makes sense that instead we travel horizontally, for instance, like in cribs, it'd be more space efficient, require less moving space.
Yeah, I think there are some also interior concepts that look at yeah. I think that's interesting, yeah. But one of the biggest issues of this flying V airplanes, like for larger numbers of passengers, is actually that you don't see you cannot see out of the windows and so on. So it's not very popular for that. So this is why now there's also maybe thinking about that for cargo transportation could be interesting, because the configuration is really very efficient. If you have a cargo airplane like this, or like Bombardier, they look at a very small version of the blended wing for a business travel, for example. So then it could be interesting because you have like a nicer layout of your living room above the sky. But yeah, it's the biggest impact on emissions comes from the long range passenger travel. And this is really the hardest also to change and to make more sustainable. So electric propulsion doesn't really work for that. These flying V concepts don't really work for that. So this is why now people investigating again hydrogen. because at least we get rid of the carbon emissions. But yeah, there's all sorts of safety concerns, and it's very difficult to have like a cryogenic hydrogen in the aircraft, and these tanks are huge, so it's 4 times the volume than the fuel, etc. So there's a it's not easy. So this is why I think we will see more advanced concepts, more like on smaller ranges, smaller airplanes. We see already the small electric airplanes for training. So see, these kind of things might come faster than really the long range passenger transport. That's the most difficult. Yeah.
When we look at the new ideas on airplanes, we can see that they're very different from like everyone. And then airports will probably need to change completely. When designing a new aircraft, the company think about like, do they expect airports to adapt to the airplanes, or do they make the airplane according to the airplanes?
Typically, there's like there's a limitation, for example, in the span of the wing that you would have, so not to change the airport. I think that one of the latest bigger development, the Airbus A380, this huge 4-engine passenger plane, and they went to the limit of that, and it was very difficult with the 2 levels, to service at the airport and so on, but they made it work. But just to answer your question, typically, yes, this is considered as a constraint, so you don't want to develop a configuration that doesn't fit on current airports and you need to change everything. But let's say if we talk about hydrogen-powered airplanes, this is like one of the major challenges is really the infrastructure of even of the fuel supply. So we don't even talk about the size of the airplanes. So it's definitely a concern. For some of these aircraft with these very long, like high aspect ratio wings, so very thin. So they're looking into some folding mechanisms, so to fold the wing when you go to airport. But this again, if you're a system engineer, you're getting a headache if you think about that. Like how do you make it that if it folds inadvertently in flight? So you need to make it really safe, so it doesn't that and so on. So, but yeah, there's it's a concern. But so typically, also we have seen commercially wise, very large airplanes are not that don't work that well. So I think they try to stay into the size of the airplanes that we already have and try to work with the. Yeah, there was a question.
The direct SVD, your power planes to be less energy.
That's an interesting question. I don't think so, but I don't know. I mean, if you can make it safe enough, why not? I think this is more for space things that probably that. Yeah. Other question.
Okay, follow us the next Susan for the.
Right, so final announcement. So our next public talk is going to be April 1st, so roughly about 2 weeks later. So the room will be Leacock 26, so it's kind of like not this building here, it's kind of on the other side of the campus. But on the email, if you have email and receive it, it should tell you like roughly where to go. So the next topic will be, is AI going to transform our understanding of the universe by Lawrence. And the final announcement, if your name is Nathan, please come and see me because you have won the raffle for the. Anyways, thank you everyone for coming.
Yes.